Good morning, folks. How's Lab 2 going? I see some, was that a head shake? Was that a negative? It's kind of a, so a bunch of people are working, I think, at this point on getting the solver integrated with an EBAB and then having it talk to the video system. Is that where most people are? Yeah. And there's a couple of aspects of this which are tricky. Mohammad figured out a way of debugging using ModelSim with the EBAB. He might talk about that today, but he's not here, so I don't know if he will or not. But basically, if you drill down into the component folder where the EBAB lives, you can get the Verilog. You treat it as a module called by a test bench, and the test bench then can pretend it is the Altera bus. So now you can simulate everything from the Altera bus outwards. And you can look at the bus traffic to make sure you're writing the correct pixels on the VGA, for instance. And since it's in simulation, you don't have to recompile every time, and it's much faster. That could be a useful thing to do. I suspect, actually, that writing pixels to the screen is fairly straightforward. But remember that my examples write the entire raster before they repeat, which is 300,000 odd points. You don't want to do that. You want to write just 2 points because you can't afford that much time writing all of those points onto the screen every time you want to put out a 1-point sample. So the tricky part is synchronizing the solver with the EBAB with the VGA display. So the EBAB can only write when VSync or HSync is low. The reason is that since the VGA screen does not have memory, it must get fresh pixels when it wants fresh pixels. And the timing diagrams, which you can look up online, show a V blank pulse during which nothing is shown on the screen. And the very next cycle, you draw a pixel. And embedded within that blanking period is an HSync or VSync. And because the H or VSync is shorter than the blanking interval, you have enough time after this to finish the write before the first pixel is required. So that if you detect horizontal and vertical sync, you can make a system which will write to the video memory but not affect the video display. So that's one piece of the synchronization, and I think most of you saw that in the demo VGA code, right? Any question on that? You want me to show the code again or no? Yes? Okay. So we go down here to the Avalon Bus Master page. Video display. Oh, and there's a new one I just did. It's video display of a video, VGA display of video input using a bus master to copy one memory to another. It took me an embarrassingly long time to get right, but I'll talk about that some other time. So this top-level module synchronizes using, of course, there's a reset phrase, and then it synchronizes by saying we're going to check for a state 0, sort of an idle state, and not VGA blank. And this doesn't work because the write takes 2 cycles. The write takes 2 bus cycles. It takes 1 bus cycle to set up the write, and then another bus cycle to check for the ACK. And because you're overlapping 2 bus cycles, you may be overlapping a pixel requirement, a read requirement of the SRAM from the VGA controller. And so this code will fail with a shimmering display. The sync will be shaky or worse. So if we use as a trigger that you're waiting for the idle state and either the VGA vertical sync or horizontal sync low, then you should get a stable display. So that's one level of synchronization that has to occur between the EBAB and the VGA memory. There's another level of synchronization which has to occur between your model solver and the EBAB. If you let the model solver just run at clock 50 or whatever prescaler you choose, then you will not be able to write all the time. In fact, you can only write when the VGA is in sync mode. Since you can't write all the time, you will miss solution states. And so you'll get a choppy looking display. The most compelling choppy looking display I saw was something that looked like this. Where, what the heck is going on here? Well, when the solver is being read out all the time, you get nice, smooth display. When the solver is not being read out all the time, you get some other state going on. So what you're going to have to do is at least 1 or 2 or perhaps more synchronization methods between the solver and the EBAB. The first method is run the solver until it's ready to plot, probably 32 solve steps, because we talked about the time scaling before. Run at 32 solve steps, stop, signal that there's a sample ready. The EBA module notices that there's a sample ready and draws them to the VGA, then signals the solver that the draw has been done. So there's a two-way handshake. So the solver is going to be running on some solve clock. The EBAB state machine is going to get, of course, data across here, but there's also going to be a data ready line. Data ready line going this way, and then coming back this way is going to be a draw complete line. So the solver runs 32 steps, stops, and asserts the data ready line. It sits there holding its output until the EBA state machine asserts a draw complete, Then it does another 32 cycles of solve. And that will synchronize it. Another possibility is synchronize the solve clock with the H-sync, so that you only clock the solver at the horizontal sync rate, so you're guaranteed to get exactly one solution point per horizontal clock. And since you can always draw during the horizontal clock, you will stay in phase. I kind of like this method better. It's kind of more straightforward in some ways. Has anybody implemented this? Sync? That's again, it's this is the hand equivalent of ish. You implemented it ish.
It works.
It works, but
Doesn't draw the right.
oh, okay. So it works, except it doesn't draw the right thing.
But it does work.
Got it. Okay. Okay, but it works. Okay, but you know that it waits the right amount of cycles. And you know, one way of debugging this is to take this line and put it on a GPIO pin, put this line on another GPIO pin, and watch them with the oscilloscope. And you should be able to watch that thing ping pong back and forth. And then on the third channel of the oscilloscope, you put the solve clock. Or put the solve clock on one, look at this GPIO. This should clock 32 cycles, and then you should get an output. This should assert, right? How do you stop the solver? The wrong answer is gate the clock. All right, you don't want to ever gate a clock. But what you could do, did you have a? No. Okay, I thought that might be the start of a hand up. But what you can do, what does it mean to stop the calculation of a differential equation? It means to freeze the integrators. So if your integrator right now has an initial condition input, it has a function input, I think that's what I called it, it has a dt input, you could have another input which is hold. And what hold does is adds one adds one stanza to an if statement. So if we go back to this little code snippet, then the integrator, if it's reset, it gets initial out. Otherwise, it gets v new. You could add one more if else. If else, hold is high. Don't do anything. Don't update. Don't update. Don't reset. And that just stops time. If you stop the state variables, you've stopped the simulation. So that's a pretty clean way of doing it with minimal modification of any of the circuitry. So 2 levels of synchronization. Solver to EBA state machine to VGA memory. Both of those have to be synchronized. Everything's running in different clock domains, so you have to do explicit synchronization. Questions? Yeah? So a few of you are to the point where this is an issue now. And the rest of you better be there by the end of the weekend, I would say. So one way to make progress is more simulation. Mohammed, did you want to talk about doing that simulation today, or would you rather not? It's up to you.
Yeah, I can do that.
Come on up. I'll give him the microphone. Yeah. Sure, yeah. So just clip this onto your shirt someplace. It's close to your, sort of right like this.
Okay.
That's where that works.
Okay. As Professor Bruce explained, the system that we currently have is something like this. So what we have here is we have our HPS here, and then we have an on-chip SRAM. So this is the bus interface. And then we have our EBAB module in here. And from the QSys, we get a conduit bus interface. So this is bus valid, then address, and write data, read data. So all those signals we get in here. And what we are doing here is we are writing a state machine in here. And we have our equation solver right here. So what we want to do is we want to give the output generated by the equation solver to the state machine, and then the state machine will write all the pixels to the SRAM, and then the VGA controller will then read the data from the SRAM and then draw it onto the monitor. So this is how our current setup is. So what I would do is instead of like directly hooking everything up and then directly watching on monitor, what I would do is I would build a separate module combining these two, the state machine and the equation solver, and then I'll write a test bench on top of this, and then I would monitor the transactions that are going on this interface. And so suppose what you would want is as soon as you like come out of reset, you should blank the screen. So what I should see that my state machine should do is it should write 0 to all pixels, like for x coordinate 0 starting from 0 to 639, and y coordinate starting from 0 to whatever 399 or 479. So it should like clear out the entire screen, and then what should happen is so this should be what my initial state should do, and after some point of time, if this is my screen, then I should set the x coordinate to 0, and then I should plot. I should write 2 pixels. I should draw 2 pixels in here, like for one for y coordinate. So there are 2 solutions coming out from here. One is x1 and one is x2. So I should draw x1 and then x2, and then I should increment the x coordinate, and then I should again plot 2 points, x1 and x2. So I should be able to see all these things running on simulation. And once like we are sure that okay, everything is running fine, then I would probably integrate the entire system and then watch things going like going on monitor. And probably I think that is a good way to, you know, instead of just keep on building systems and then like it takes 10 minutes and then you don't see anything on VG and you are stuck with your debug. So I think like one way to go about these things is to just take your state machine, take your equation solver, do some simulation, and then you should be able to probably monitor what transactions are going on, and based on that you should figure out what you are doing wrong.
Didn't you also include the EBAB in a simulation also?
Oh no, so it is.
You didn't? I thought you
yes.
put the EBAB
no.
in there.
No, I just integrated the state machine and the equation solver, and I monitor the bus transactions that is going on over here. So how I get the x coordinates and the y coordinates is I have the address, And so the address consists of like the 19 to 10 bits are the y coordinates, and the 9 to 0 bits are the x coordinates. So I look at the bus address. So from there I get the x coordinate and the y coordinate, and then I look at the write data. So write data, if it is 0, 0, that means I'm erasing a pixel. And if I'm writing like 0, 3, then I'm drawing a blue pixel. If I'm writing E0, then I'm writing a red pixel. So what I can do is probably I would, for x1 I would write 0, 3, and for x2 I would write E0. So based on my simulation, I would get to know that I am writing correct values for x1 and x2, and I would like go about from there. Okay. So if you have any questions, you can like post on Piazza, you can talk to me, and then
Use Piazza.
yeah.
Thank you. So, questions about sync? Questions, anything more about Lab 2?
So I know in the past you went over how we convert from, or how often we should sample the solver to get a correct number of periods. So,
Do you want me to do it again?
I mean, kind of, if that doesn't take too long.
No, it doesn't take long.
In the case that, for example, we sync it so that each sync, how will that affect?
So, what I said was I want a few cycles across the screen. So if we look at the VGA, after you've cleared the screen and drawn a screen full, there should be a few cycles, whatever few means. To me that means something like 6 or 7 or 8 or 10, but not 1 and not 30. So this might be, let's call this 2 to the 3rd cycles across the screen, 8 cycles across the screen. So we have 640 points to do 8 full cycles, which suggests, so that's 640, well, let's call it 512, it's close enough. So we have 2 to the 9th over 2 to the 3rd, so that means it's about 2 to the 6th points per full cycle. Right, so now we say, how many points per radian should we have? Because the natural time units for, or the natural frequency units for the solver is radians per second, not cycles. So you divide that by 6, and you get something like 10 points per radian, or something of the sort. So that would suggest that if you do that, and you have a k over m of equal to 1, which means 1 radian per time step, 1 radian per 2 to the 9th time steps. Let's see, so you want to have, so you want about 10 points out from the solver per radian, right? To the screen. And how many steps are there going to be in the solver for 1 radian? If k over m is 1, and you've taken a delta t of 2 to the minus 9, you get to choose this, but I'm suggesting 2 to the minus 9 is a good number. You might use 2 to the minus 8, certainly not a smaller number than that. Then you need 10 solver steps, and in 1 radian you're going to get 512. That suggests that you ought to sample about every 50th point of the solver. Well, 32 is pretty close to 50 on a log scale, so we'll call it 32. But it could be 64. Or you could make it a parameter settable on the switches, so you could choose the scale without recompiling. that clear?
Yeah.
So, you're generating a lot of points per time step because the integrator is not very good. Or their integrator is not very good, so you have to take little time steps. That means that you're going to have to select about every 30th or 50th point, something like that, for plotting. Otherwise, all you'll see on a 512 screen is 1 radian. Whoop. Okay? Anything else on Lab 2? Say again?
The sign that was wrong on the chart.
It's not wrong, but it's misleading. So, thank you. So, there's a negative sign here. And in the MATLAB code, no, not that MATLAB code. This MATLAB code yes. There it is. In this MATLAB code, if you look carefully, the force here is positive, and the reason is that the x argument is already negated by the subtraction here. It's right wall minus x, and so we've already negated it once. If you negate it again, the symptom will be that the integrator is unconditionally unstable. And so what you will see is that spring 1 is going ring, ring, ring in the so this is x1, v1 looks like phase 190 degrees out of phase more or less, and x2 is looking like this. That's a rough representation. That is a sure sign that you've got the SIGN of an integrator backwards, because it's doing nothing but overflowing as fast as it can. Thank you. What else? So again, I can answer more questions about Lab 2. It's a little late to start talking about the nonlinear wave equation, so I'll probably wait till next Monday for that. But you are going to have to read up on, and you can do this simultaneously. For instance, when you're waiting for the compiles, you could read these papers. You might also read documentation on incremental compilation, although I've set up most of the projects to have partitions that are hidden from you. You can look at the partitions using the partition manager to see how they're partitioned. We're going to be using the Wolfson codec, which is mercifully hidden from you behind the audio input-output abstraction layer. But this is a completely separate piece of hardware on the board with its own state machine, which occasionally gets hung up. And it turns out that if it gets hung, you can't unhang it except by cycling the power. And on our boards, you must bring down Linux before you cycle the power. So you'll have to unboot, recycle, and come back up again. So hopefully that won't happen. I haven't seen it happen yet on these boards. The old boards had it happen about 1 time in 10. But we're going to be accessing the Wolfson codec through the University Audio Core, which is the abstraction layer that is available on QSys. So you'll be interfacing to a QSys module in which you're going to take your drum output, your simulated drum output, submit that to the audio codec with its own synchronization and bus requirements. And then it will be output. Now, there's another, the codec runs at 48 kilohertz, and so there's another synchronization step, which is the bus speed down to 48 kilohertz, so there's a big FIFO that you have to manipulate. But that's well documented in the core manual for a change. And so it's not so bad. So the next step in doing this, in talking about this lab, is to talk about the nonlinear wave equation. So I think I won't start that. Let's talk about final projects for a little bit. Who's got an idea for a final project? It's only about 3 weeks away. You have to write a proposal. Turns out that the video input. So if you want to get video into this thing for doing analysis on, that's fairly straightforward. I say after screwing around with the thing for a week. So there's my smiling face captured on video. The only artifact, it's 8-bit video, so the colors look like butt. However, that's the VGA interface. If you don't go to VGA interface, if you merely record the image into image memory, but don't decode it back to VGA, you can store 16-bit images. Or you can do grayscale. The only artifact that's so far left is that the image moves up and down 1 pixel relative to the VGA sync. It's just enough to say, yeah, I wish it wasn't doing that. So I'm trying to figure that out still. And as far as I can tell, it is not the interface from the capture memory to the VGA display memory, but rather it's the interface from the video capture to the static RAM that holds the captured image. So I don't know what's causing it yet. But the circles here, the disks are all drawn by the HPS, by the ARM. So you can simultaneously draw to the screen from an EBAB, which is copying the capture memory into display RAM, and you can write to that same display RAM from the HPS. So you can superpose graphics onto your image, but this is really just a proof of concept that I know how to, that I actually know how to read the image. And probably what you would do if you were trying to build a game that does, say, image or gesture recognition is, you wouldn't bother to put this image back out to the VGA except for testing. You would only use the image to calculate some set of moments based upon where the hands are and some image recognition stuff. The basic codec is 320 by 240. It's not bad. It's a reasonable size for lots of game control. So think about game control or video control as an input for a final project. What would be very cool would be to use one of the neural net frameworks which is available and see if you could do image recognition coming in through that interface. Hold pictures of the cat up in front of the camera and pictures of cars and see if it can generalize across. See if you can make a system that generalizes people versus not people or whatever you want to do. That would be a very cool project. So I tried something new here on this. So where I talk about adds a bus master which can read from the on-chip SRAM, I decided I would make a little cartoon thingy. It took me an embarrassingly long time to figure out how to capture a tooltip window in Windows. I was almost reduced to taking a photograph with my cell phone. And it turns out that snippet tool doesn't work. Control save screen doesn't work. It saves the screen, but not this window, not this little panel. But alt function save screen does. It took me an hour to figure out. But what this does is allows you to then. So what I'm doing here is trying to figure out a way of showing QSYS connections without showing the whole damn diagram. And what this is my EBAB video in master connected to the slave 1 input of the on-chip RAM, slave 2 input. And the video input controller then, the video input controller is wired to the S1 slave, the other slave, so that you can simultaneously do video in read or video in write and EBAB read. You can also write to this memory from the EBAB if you want to do really unusual captures. You can capture an image and then write on it. So that's how I'm going to try and do the documentation for QSYS now. And I put enough screen over here so you could see the base address because that's important for how the system actually works. So you've got video in, you've got video out in the form of VGA. You've got Ethernet. So you could, in principle, let's say you were doing some head-related transfer function, you could read the MIT head-related transfer function database in real time, download the coefficients to the FPGA, and do a surround sound kind of virtual acoustic interface while maintaining very little state on the FPGA itself. That'd be cool. So you use the FPGA for the fast finite impulse response filters that are required for both ears. You use the HPS as a way to get data quickly to figure out what to do. And if you don't want to actually download the database in real time, which is always iffy during a demo, you have enough dynamic RAM on the HPS side that you just put the whole table in RAM or on SD card and load it into RAM when you're ready to do the demo. How many people have backed up their SD card? Good. Do it. Because it will fail. And it fails weirdly. Sectors go bad. Blocks go bad. Linux just compensates, says, can't read that one. Boom, gone. Takes it off the list until suddenly you can't compile a program. Or some other thing fails. Or worse, the swap memory gets corrupted. And then you're done. So back it up early. Okay, final projects. Any ideas for final projects? Yeah.
I was thinking like video input with a person talking, and they could like bleep out like certain words and also like draw a box over their mouth like real time.
This is for the alternate fact kind of generator, yeah. That's fine. I mean, one of the projects that was done a couple of years ago was the video anonymizer. You know how faces are kind of sometimes pixelated? They did an automatic face finder pixelator. So no matter how you moved in the video, it auto-pixelated your face. That's cool. And so what you want to do is take it into the audio domain by detecting certain patterns and replacing them with something else. The 7 words you can't say on broadcast television, for instance. According to, who was that? George Carlin? Was that? Yeah, that was, I think is who came up with that list, right? Look it up. I'm not going to play that video. I'd go for that. Yeah, I mean, a mouth tracker. The way they were doing skin tracking, the way they were doing face tracking, was they were looking for a large connected blob that had the appropriate vector location in color space. So, as you know, in humans, color space is 3-dimensional because we have 3 color detectors. A long wavelength, a medium wavelength, and a short wavelength, red, green, and blue. And the way the video is encoded coming off the camera, it's actually encoded as an intensity channel, and then 2 color difference channels, one being more less red, green, and the other kind being a yellow-blue axis. And so the intensity carries the brightness, and these 2 carry the spectrum. It's the best spectral estimate you can do with 3 channels, is 2 spectral components. After you've subtracted out the brightness, after you've actually divided out the brightness. A whole bunch of research has been done on what skin looks like in this space, which we'll call YIQ space. And it turns out that if we look at this, there's a small area of the IQ phase space which maps almost everybody's skin. The reason being, there's a single pigment with a single chemistry that determines skin color independent of intensity. And so everybody's skin maps into about the same region, and it's fairly unique in terms of what else you see in the room. And so you can map faces by looking for large connected regions of this face space. So it's a very fast way of doing not face recognition, but face finding in the image. It gives you a real rough estimate of where the blob is. Now, if you want to do something fancy, like get rid of the, put Teddy Roosevelt's teeth in your mouth or something, then you have to get pretty accurate with the mouth. And so now, once you find where the general blob is, then you're going to have to look for mouth corners in that image, and maybe eye corners, because that's pretty standard among humans. Eye spacing is pretty standard, between 55 and 65 millimeters. So once you get some fiducial points, then you can do some precision mapping onto the face. But, and you might want to do that. There's another thing you can do. If you do precision mapping of about 100 points on the face, then you can do things like interpolate between your face and Teddy Roosevelt's face, or your face and George Bush's face, or whatever you want, because those measurements on standard faces are known. If you know the measurements for your face, you can distort one face into another. And you can then have a slider that says, I want to be 50% Marilyn Monroe. Right, and so that, yeah, that it could be cool. It could be fun to do that.
What about the audio component of that, recognizing words?
Recognizing words is hard. So there's the basic technique is that you come up with a short-term spectrum. And it turns out FFT doesn't work very well for speech. That really what you want is a filter bank which is spaced linearly at low frequencies and logarithmically at high frequencies. It's called a MEL spectrum. And I don't remember what that stands for. So you resolve the signal into a MEL spectrum with a time constant of, say, 20 milliseconds. So that if you wanted to do 1 second of speech, you would have 50 MEL frames all lined up next to each other, where now this spectrum is one of the vertical columns here with a color proportional to intensity or some sort of intensity. Now you have a two-dimensional array of intensities, frequency in this direction, MEL frequency in this direction, time in this direction. Then you use a neural net or some other machine learning to map that onto a word. That's the basic idea. There's another piece that you need because people talk at different rates depending on millisecond to millisecond context. And so you have to often do what's called dynamic warping before you do this process to put everything onto a constant time scale. But the basic idea is you're going to do a two-dimensional map of frequency, intensity versus time, and then treat that as an image and recognize it. It's non-trivial. The best I've seen in the microcontroller course was 6 words that was recognized. The best I've seen in the FPGA course, in this course, was a system that did not detect words, but rather could identify speakers independent of what they spoke. And because you talk to your mom on the phone, no matter what she says, you know it's your mom, right? And so what is it about voice that that makes you able to recognize the person independent of what they say? I mean, if they're saying you don't call me enough, then you know it's your mom. But it never changes, by the way. But what is it about the dynamic system, which is your voice production system, that is unique to you? And there are some mathematical models of that too that I'll go into if somebody wants to hear about them. It's called the MEL sepstrum, which is spectrum spelled inside out. I'll be in lab this afternoon. For the rest of the semester, I'll probably be in lab on Wednesday afternoon and Friday afternoon. I can be there Thursday afternoon too if people want. It's nice for you to get some other work done, but my first priority is to teach the course. Right? So let me know.